Yesterday, when we left off, we were talking about change, and of course, one of the ways that we determine that change, whether it be physical or chemical change is occurring, is to make some observations or measurements. And so we have two ways of measuring change. One which we refer to as qualitative. And of course, qualitative is something that we talked about yesterday as we looked at some of the chemical reactions, and the way we determined that in fact they occurred was qualitative indications. For instance, the formation of a colored gas from two non-colored gases, the formation of a solid when we combine two solutions, the formation of a gas from reacting a solution and a solid. We would refer to those measurements as qualitative. So such things as color, change in physical state, etc. would be then qualitative measurements. But more cases, we have to do the measurements quantitatively to tell that changes are occurring. And so this is what we're going to look at quickly here, the units that we use in science to make quantitative measurements. The 5 things that we typically are interested in measuring are the mass of a chunk of matter, its volume, and yesterday we talked about density as being then mass of a matter divided by its volume. So those are two then properties that we should be able to measure, mass and volume. Length, when I say length here, I'm talking about all dimensions, so we mean length and width and height. So just whatever measured dimensions we could make in that type of measurement. Temperature, because as I indicated in a previous lecture, that the change in matter, whether physical or chemical, always involves energy. And of course, one of the ways that we measure that energy is flowing out or energy is flowing in is to measure the temperature of a material. So measuring temperature. And then, of course, time. If we're talking about, for instance, later on we'll talk on a chapter of what we call the rates of chemical reactions. And that's going to involve time. How fast is something produced? Moles per second, moles per liter per minute. So time is a measured quantity. Now, in the metric system, the scientific system, of course, these have then certain units that we assign to them. The base unit for mass is the gram, and we use a lowercase g for mass. For volume, the basic unit that we use is the liter, and the symbol that we use is the uppercase L. For length, for dimensions, the base unit is the meter, and we use a lowercase m for that. For temperature measurement, the standard temperature scale that we use most of the time in measuring temperature is the Celsius temperature, and we use a capital C with a little superscript naught to indicate degrees Celsius. Time, we use S, lowercase s, which stands for second. Okay? Now, in science, we often are working with either large quantities or very small quantities of material. And so frequently then we have to express large amounts or small amounts of these measured quantities. And that's what makes the metric system so nice. Those basic units there are the units that, of course, cover any time we are talking about mass, large or small. Gram is the basic unit. We can then use some prefix to talk about big and small, which we use powers of 10 then as multiples of these basic units. So everything is the basic unit, and then any other measurement, large or small, is merely multiplied by 10 a certain number of times or divided by 10 a certain number of times. There are some prefixes that we should be familiar with that we'll need to use throughout the course, and these are given to you on table 1.6 in the text, and let's just look at those quickly. The basic unit, of course, is 1, so we're not showing a 1 on here. That would be the grams, that would be the liters, that would be the meters. If we wanted to talk about 10 units of something, like 10 grams, we use the prefix deca. So decagram would mean then 10 grams. Or if we wanted 1,000 grams, the prefix for 1,000 is kilo, K-I-L-O, and the symbol that we use there is the lowercase k. And for deca, D-A. Or if we need very large amounts, if we're talking about, for instance, the energy released in an atomic weapon explosion, it's usually expressed in terms of megatons, which means then millions of tons equivalent dynamite. So if we had a 15 megaton bomb, it would mean that the bomb would produce the same amount of explosive force as 15 tons of dynamite. That's what we're talking about. So mega, of course, obviously is a large value. Also, if we talk about electric production at power plants, we talk about power plants in terms of megawatts of energy that they can produce. So mega is a large unit. There are bigger ones than this, obviously, but these are the ones that I expect that you should become familiar with. Now, below the unit 1, then we have smaller divisions, and the first is deci, which is 1/10 of something, or putting it into a decimal representation, 0.1. So a decimeter would be 1/10 of a meter. A decigram would be 1/10 of a gram, etc. So these prefixes can be used with any of those measured quantities that we just talked about, grams and liters and meters, etc. And putting these prefixes in front then gives us a large or a small measured quantity. Centi, 1/100th, or 0.01. Milli, a little m, for 1,000th of a unit. Micro, which is getting quite small now when we talk about micro, which is 1/1,000,000th. So we're talking about 0.0001 unit. And nano, which is getting very small, as you can see, then 1/1000,000th, or 10 to the minus 9. Now, nanometers are a unit that we use when we talk about the length of electromagnetic radiation of light. Visible light has a wavelength of about between 400 and 700 nanometers. That's the term that we use to talk about that. Okay? Milli, matter of fact, these 3 units right here are basically our money system. The United States is sort of an odd country from the standpoint that we tend to refuse to use the metric system for measurement, but we're one of the few countries in the world that had a monetary system that's always been based on the metric numbers. We have 1/10 of a dollar. That's called a decidollar or a dime. We have a centidollar, called a cent, or we sometimes call it a penny, and that's just a carryover from the Old English, our relationship to England, which had a pence. But the pence in England had nothing to do with being 1/100th of anything. It was just a coin called a pence. But in America, then a cent is 1/100th of a dollar. And a mill is 1/1000th of a dollar, and that's exactly what you are charged if you're going to pay taxes. You pay a mill levy. A mill levy has nothing to do with grinding corn. Okay? It's not a milling process that we're talking about. We're talking about you're charged 1/1000th of a dollar, or some number of thousands. If your mill levy was 100, it would be 100,000th of a dollar for every X dollars that your value has. That's a mill levy. That's how we pay taxes on real estate. So we have a metric system for our monetary, and yet we tend to try to resist using the metric system in terms of our measured quantities. We're about the only country that doesn't fully use the metric system for roadsides and speedometers in the automobile. We're moving that way, but we still tend to resist. You might, this right here, a millimeter, that's kind of an interesting one, because a meter is about a yard. Okay, it's a little bit longer than a yard, and we don't worry about the English metric relationships. If we need it, we have a table in the back of the book. But a meter is about a yard. Okay. Now, there was a commercial. I don't know how many have seen it. It's not too old. Benson and Hedges cigarettes. Anybody ever remember seeing Benson and Hedges cigarettes commercial? At least one person. They used to advertise their cigarette and talk about that the cigarette was a silly millimeter longer. Now, typical king-size cigarettes are 100 millimeters in length. That's the commercial way. Benson and Hedges, to have a little upsmanship in their sales, made theirs 101 millimeters in length. Now, at that millimeter, you wouldn't be able to tell. That's about that. If the cigarette pack got dropped, you would compress more than that. But the essence of the ad was the person would put a Benson and Hedges cigarette in and happen to turn to close the car window, and the car window would catch it. Or they'd step onto the elevator and the elevator doors would shut on it. I mean, implying that you were getting a whole lot more cigarette because theirs was 101 millimeters. But they also said silly millimeter longer, and that was true. That 1 millimeter had nothing to do with all of these things that they were applying it to. So we do see the use of these in different areas, and these are the ones that especially centi, milli, and kilo that we use very frequently that we should certainly be familiar with. As a matter of fact, this one here, kilo with gram, a kilogram, is usually abbreviated in the news as a kilo. So when we hear that the police stopped a car on Interstate I-44 and they found 10 kilos of marijuana, what does that mean? They found 10,000 grams of marijuana. That's what it means. A kilo is 1,000 grams. Okay? Or to put it in perspective, a kilogram, 1,000 grams is about 2.2 pounds. So a 10 kilogram bust would be then about 22 pounds of marijuana. All right. Now, the other thing that you'll note over here is that these numbers have also been written in what we call scientific notation. And we frequently use scientific notation in chemistry to write large and small numbers. To write a number in scientific notation, for instance, this number here, written as a decimal and then as scientific notation. Scientific notation is written with one digit first, a decimal point, then whatever other numbers would fall after, in this case zeros, multiplied by 10, and then either to a negative or a positive. If it's a negative power, it means that to convert then this number right here in front of the time sign back to this one, we would have to divide. That's what the negative sign implies. We would have to divide the number by 10 9 times. Or in other words, we're going to need to move the decimal point 9 places to the left. So the negative sign would mean we're moving the decimal back to the left 9 places in order to get back to our original number. If we go right here and put the decimal here, we're going 1, 2, 3, 4, 5, 6, 7, 8, 9 places back to the left then to give us back the original number. And as I say, we do use scientific notation quite extensively in writing numbers in chemistry, so you do need to become familiar with those. And I think I had a problem to look at the end of the chapter. Yes, I do. Problem number 7 at the end of the chapter as an example of writing some numbers in scientific notation. And I'll just go ahead and do that right on the bottom here. The first number is 507.4.8. Now, if I wanted to write that now in scientific notation, I'm going to write it as 5.0748 multiplied by 10. Now, in this particular case, because the number is bigger than 1 and we're moving the decimal in the first place to the left, the power of 10 is going to be positive. How many places did we move it? 3, so this is 10 to the third. In other words, if I take this number here and multiply it by 10 3 times, the first time I multiply by 10 it would be here, the second time here, and the third time here, and we're back to our original number. So a positive power of 10 implies that we're going to multiply by 10, or in other words, we're going to move the decimal point to the right. Positive means we're moving the decimal to the right. A negative power means we're moving the decimal to the left, that number of places. All right? Any question on that one? Let's look at the next one here. 0.016050. And we want to write it in scientific notation. Now, I'm going to need to move the decimal 2 places there, so I'm going to write it 1.6050 times 10. Now, in order to put the decimal back where it was, we would have to move it back to the left, wouldn't we? So it's a negative power, and how many places did we move it? 2. And so 1.605 times 10 to the minus 2 would be the correct number written in scientific notation. And let's see, well, we can just look at one more here. 14176, this is part D on number 7 at the end of the chapter. We're going to, the decimal really is there even though it isn't shown, and so we're moving it 1, 2, 3, 4, 1.4176 times 10, and we moved it 4 places, so times 10 to the 4th. All right? Any question on writing numbers in terms of scientific notation? Okay, there are several example problems in the book. There are also some problems at the end of the text that you can try to see if you do understand it or have any questions. Okay. Now, whenever we measure something, there is always an uncertainty relative to the measured value. In other words, no scientific measurement is totally exact. No scientific measurement is totally exact. There is some degree of uncertainty in that measurement. Now, when we write down the numbers that we have measured, we should write down only the numbers that we're justified in writing down based on the measuring device that we are using. And those numbers that we can justifiably record are referred to as significant figures. Significant figures are then all of the numbers that we have actually measured plus one uncertain number. Not 5 uncertain numbers, one uncertain number. Those are called significant figures. What causes this uncertainty in the measured quantity? Well, there are several things. Number one, human error. If we typically read looking down or up at a measuring device, we may read an error. Some of us have a tendency to always read on the high side of a measuring device, and some would tend to always read on the low side, so we've built in again a human error. But in addition to the human error, if we don't properly calibrate the measuring device, we already have a built-in error and mechanical limitations. I think probably a good example is a bathroom scale. If I have a digital bathroom scale and I step on that scale, it may show a weight of, say, 160 pounds. Now, I can't record my weight as being 160.0000. I didn't measure that. I measured 100, I measured the 60, the 0, the last number I see down there is still uncertain. It's uncertain because obviously that bathroom scale has some degree of mechanical limitation and some degree of uncertainty of calibration. So I'm pretty sure that I weigh at least 159, and I probably weigh, or no less than 159, and I probably do weigh at the maximum 161. A bathroom scale gives us then an uncertainty of plus or minus 1 pound as a measuring device. So if I use that to carry out scientific experiments, I can't record hundreds of pounds or thousands of pounds, whatever the case might be, because my measuring device has that degree of limitation. Now, one of the measuring devices that we use quite extensively, and you'll be using if you're in 105, which a good share of you are, is what we refer to as a centigram balance. Centigram, centi means 100th gram. This balance has a mechanical limitation of weighing only to the nearest 100th of a gram. So if I were to weigh some chemical here, let's say on this centigram balance up here, the scale doesn't show real well, but I do know that that one is in the 50 position, and these are units of 1 across here, so it looks like it's setting on the 9. And then these are tenths. It's a little hard to see it. And in between the tenths are another division which gives us the 100th. So we could probably then say that the mass over here was 50 and the 9 is certain. So I'm certain of the 50 and I'm certain of the 9 and I'm certain that it's between 0.2 and 0.3. So I put down 0.2. And then I'm going by some little mark in between, and I'm not quite sure which one it's closest to. We'll just say, in this case, 4. And so I would record then the mass as 59.24 grams. Or in other words, we have 3 numbers here that we're certain of, and a 4th number, which is my first uncertain, and all 4 of those measured numbers then are referred to as significant figures. Okay? The number of significant figures we can put down then is limited by the measuring device that we are using. If I use a balance called a milligram balance, that means that it can weigh, mechanically, it can weigh to the nearest 1,000th of a gram. And if that were the case, I would be justified in recording then another digit there. Okay? Now, oftentimes, however, in problem solving in the book, we are basing our number of significant figures, then of the measured quantities, on numbers given to us, not ones that we've gone to the lab and measured. As a matter of fact, for those in the 105, your second experiment that you do is an experiment strictly looking at limitations and using significant figures in scientific calculations. So you'll get quite a bit of experience on this in experiment number 2. But if we are depending upon somebody else's measured quantities, we do have some rules that we use to determine the number of significant figures in a number. These are just slightly, I think the first 3 are in the same order as in your text, but the next ones are interchanged, but they all give us the same information. What numbers are significant? First of all, rule number 1, all non-zero digits between 1 and 9 are significant. And here we have some numbers given. The number 1, 2, 3, that has 3 significant figures in it. The next number that we see up there, 4.5678, that has 5 significant figures. All of those are assumed to be measured numbers. Okay? We don't know what they measured it on, and so if it was a recorded number, we're assuming that they're applying the proper rules, and so we would then use all digits as significant. And of course the number 9, if that's all that was recorded, we had 9 apples, we have 1 significant figure. Okay? All zeros between non-zero digits are also significant. And here's some examples of that. The number 10203. Notice that those 2 zeros fall between digits, and so they are in fact measured quantities. They're not just accidental, they're measured quantities. We measured 10,203 units of whatever it was, grams or meters or apples or oranges. So we have 5 significant figures in that number. The third rule, all zeros preceding the first non-zero digit are not significant. This occurs when we see a number like this, 0.049. All right? Those first 2 zeros do not fall between digits. And by the same aspect as we were applying Rule 2, zeros between digits are significant, zeros not between digits and not following a digit are not significant. Okay? Now, the way we get around this, and the best way to look at it, is to always write our numbers in scientific notation. Notice if I rewrote this number here in scientific notation, we're going to move the decimal 2 places to the right, so 10 to the negative 2, 4.9 times 10 to the negative 2. We just look at the number 4.9 and we can see that we have 2 significant figures. So it's usually best to write numbers in scientific notation when we're trying to work with significant figures. Here's another example, 0.00709. Now if we rewrite it, you see these zeros, these 3 zeros here are not significant. They're not between digits. They're not preceded by a digit. So they're not significant, but that 0 is significant. It's between 2 digits, rule number 2. And so we would have then, if we rewrote it in scientific notation, 7.09 times 10 to the minus 3, we can easily see then 3 significant figures. The fourth rule on this, and it may be the 5th in your text, I can't remember which way that it was written in there, zeros following a decimal point are significant if preceded somewhere in the number by a non-zero digit. When we look at this number here, 3.400, those 2 zeros are significant. Whatever the measuring tool was, allowed us to record exact zeros on the end. In other words, if we were using a milligram balance, a balance that allowed us to weigh to the nearest thousandth of a gram, if it weighed exactly 3.4 grams, it would give us numbers of 3.400. In other words, we're certain of the first zero and uncertain of the second, but that's still a significant figure. All known numbers plus one uncertain number. Okay? This one has a bunch of zeros in. This zero is not significant. Rule number 3. This zero is significant, rule number 2, because it falls between digits. And this zero is significant because of rule number 4. It is preceded someplace in there by a digit, and it occurs after a decimal point. So it is a significant, and so therefore we would have 5 significant figures in this number. Okay? All right, a couple of other rules here. I think you're in the book, rule number 5 is this rule number 6. An exact number as defined in certain conversion factors has unlimited number of significant figures. All right, if we have defined something. In other words, we've defined that there are 3 feet in a yard. That's by definition, 3 feet in a yard. That means that there are exactly 3 feet in a yard. There are 100 cents in a dollar. So there's not 100-point question mark, there's 100.0000000, whatever number of zeros you want to infinity, cents in a dollar. It's not a measured quantity, it's a defined quantity. There are 12 inches in a foot. There are 1,000 meters in a kilometer or kilometer. Those are by definition. They have unlimited number of significant figures. Okay? Well, as we go along and work problems, we're going to emphasize very strongly the importance of recording answers and numbers to the correct number of significant figures, especially in your laboratory work, because you will be making the measurements. You will know the limitation of the tool that you're using. And so those numbers are important when you record them. Yes, we have a question in the back there. All right. The question was, could I re-emphasize this last one pertaining to a defined number? Again, if we say there are, 16 ounces in a pint? Quart. Pint. Okay. See, I'm not good at the English system. There are 16 ounces in a pint. That's not a measured. That's by definition. Somebody said, we will say 1/16 of a pint is an ounce. All right. By definition, there are 2 pints in a quart. Again, that's strictly by definition. All right. And so any number that is something that is merely by definition, not a measured quantity, has unlimited number of significant figures. Whatever you want to call it, 10, 100, 1,000, it's whatever it is, okay? All right. Does that answer it? All right. Any other questions on that? Okay. Now, when we calculate an answer, and often this is what we're going to be doing, the calculated answer has to pay attention to the significant figures that we have used in the calculation. The general rule of thumb is that if we are multiplying and dividing, that the answer for the problem cannot have more significant figures in it than the number with the least significant figures in it used in the problem. Now, another way that we can kind of think about this limitation on our calculation is we could say that a chain is no stronger than its weakest link. I mean, I don't care how big the links of a chain are, its strength is going to depend upon its weakest link. If I take a little piece of flimsy wire and tie a couple of the links together, and then I have great big links the rest of the way, the strength of the chain is going to depend upon that weakest link. The accuracy of our answer depends upon the weakest number that we have used. Weakest in terms of number of significant figures used in the calculation. So our answer can't be better than what we have used to make the calculations. That's very important to remember, again, especially in your laboratory work. Now let's take a look at what we're saying here and how we apply that then. Let's suppose here in this first example now that we're going to multiply 3.63 by 5, 6, 7, 8, 9. Now if I use my calculator, if you punch this in on your calculator, what you're going to see on the display is a number 206,144.07. And you might have a tendency to want to write that down. But that is not correct. That is not a correct answer, because what that's implying is that we have, if we look at the number of significant figures in our answer, we're showing that we have an accuracy of 1, 2, 3, 4, 5, 6, 7, 8. We have 8 significant figures in our answer, which would imply that the numbers that we use to get the answer had an accuracy of 8 significant figures each. And it doesn't. Yes, we have a question again.
What were those numbers?
Which one?
What were the numbers multiplied?
3.63 multiplied by 5, 6, 7, 8, 9. Okay. Maybe that's a little out of focus there. All right. Now, how are we going to actually write our answer? Well, our answer shouldn't be any better than the poorest number that we used. All right. How many significant figures in the first number that we used? 3. Okay. They're all digits. Rule number 1 says that all digits are significant. How many significant figures in the second number we used? 5, 6, 7, 8, 9. 5 significant figures in the second number. Our answer should be limited to how many significant figures? 3. Good. The poorest number that we used. Well, now if we do that, then what we're going to have to do is first of all rewrite this number in scientific notation. So notice I have moved the decimal now 1, 2, 3, 4, 5 places over, rewrote the number 2.0614407 times 10 to the 5th. And maybe I can go ahead and write that again here. If it isn't real clear for everyone, let me rewrite it so we can see it then. 2.0, but I have to be able to see it. 614,407 times 10 to the 5th. We said that we're going to be limited to 3 significant figures. So I start from this side and count over 3 significant figures. That's 1, that's 2, that's 3. Now I'm going to draw a line right there. Now we apply the rules of rounding off. If the number after the last number we're going to keep, in this case the last number we're going to keep is the 6. If the number after the last number that we're going to keep is greater than 5, we round up. We would call it 2.07. If the number after the last number we're going to keep is less than 5, we will drop everything after the last number. In this case, it's a 1, and so obviously we're going to just throw away everything after the 6. There are those very few cases where you might plug in and it comes out to be an exact 5, 2.065, and that's what it shows in the calculator, meaning that everything else are zeros. All right? What do we do then? Well, the general rule of thumb for rounding off numbers is that we always round so that it's an even number. Seeing that 6 is already an even number, we would drop the 5. Let me just write up two numbers here to show what I mean. If we had an exact number here of 2.045, because the number preceding here was already an even number, we would drop it. If our number was 2.075, because it's an odd number, we would rewrite it as 2.08. In other words, we're always going to round an exact 5 so that we have an even number. You see, what we have done is we have thrown it away and kept it an equal number of times. So statistically, we're not impacting our answer. Back to this one, however, then, because it was a 1, less than a 5, then we're going to merely throw that part of our answer away, and the final answer properly written would be 2.06 times 10 to the 5th. Now it shows 3 significant figures. That's what we must have in the answer. Okay? Yes?
What do you do if there's not just zeros after the 5? Like if it's 2.07532.
All right. The question was, what do we do if it's not an exact 5? Is that what you were saying?
There's numbers after the 5.
Okay. Well, then it just goes back to the basic rule that if it's over 5, anything over 5, okay, then we're going to round up. So in other words, if we had a number that looked like this, 1.465, 0.000000001, you better not have a calculator that does that much. But if we did have, and we're going to 3 significant figures, that is greater than a 5, right? 5 plus number zeros and a 1 is still bigger than an exact 5. We would round up. Okay? We would now round our answer up. That's not going to happen very often because your calculator is going to have a fixed number of spots that it can display, usually typically 7 to 9. And most calculators do not display zeros. In other words, in the calculator, if I had a 2.075 for a number, it will not show 0000 out the other places. So if nothing shows up on that calculator screen, that means that that's exact zeros from there on out. Okay? Otherwise, it would display something. Okay? All right. Any question on that idea of significant figures involved in multiplying and dividing? Multiplying and dividing, our answer is limited to the poorest, we'll call it that way, the poorest number we've used in the calculation, merely meaning the one with the least number of significant figures. But now, in addition and subtraction, we have a slightly different rule that's applied, and so we need to keep that in mind. In adding or subtracting, it really depends upon the numbers after the decimal point that we're concerned with. We must maintain the same number of digits after the decimal point in the added or subtracted answer. The same number of digits after the decimal point as the poorest number that we have used. Okay, not the number of significant figures, the number of digits after the decimal point of the poorest number that we have used. In this particular case, the first example, every number has one place after the decimal point. Our answer should have one place after the decimal point. All numbers preceding the decimal point are significant and are kept. So note what happened here is that in this particular case, when we added these three numbers together, the first number had two significant figures, the second number had one significant figure, the third number had two significant figures. When we added them together, we got an answer which has how many significant figures? 3. 18.7. All of those numbers would be kept. Only after the decimal point that we're looking when we add and subtract. And very quickly then, because we need to wrap up, let's just look at this one here for a subtraction. We have a 0.8, and we're subtracting a 4.658, and this is the number that we would get. But how many places are we justified after the decimal point in our answer? Just one, because that's all that's in the first number, the 10.8. And so my answer, my correctly written answer would be 6.1. So we had 3 significant figures and 4 significant figures, and we ended with an answer with 2 significant figures.